I will begin with a word of prayer. Heavenly Father, we thank you for this day. And again, Lord, I thank you for these students. Just help us to discover some new things today, Lord. In your name we pray. Amen. Okay, so we found that, and I guess we found it before break, right? But that's a pretty neat example. I'm really happy with that example. But as we've talked about, it's totally possible that we could look at, so more generically speaking, suppose that A is, an n by n matrix over some algebra, right? And then we're looking for a function. I'll use vector for just a second. So this is a function from A, right? From A to n tuples, such that what? Such that dr, the algebra variable, is equal to A times R. Like that's the, the system we seek to solve, right? And here, of course, this algebra could be all kinds of different things, right? It could be, well, we studied last time R cross R. It could be hyperbolic numbers. It could be these things. The null numbers. It could be the n hyperbolic numbers that we talked about before. It could be the n dual numbers. It could be the complicated numbers, I think is a notation. So this basically just so sometimes the complicated numbers are just the hyperbolic numbers because there's an isomorphism between them for certain n. Because if you have something that cubes to 1, you also have something that cubes to -1. So there's some these are not distinct cases, the complicated numbers and the hyperbolic numbers. There's some sort of intertwining between these things. And then, of course, you've just got the wild world of group algebras. Pick any finite group you like. Form the group algebra. That's an algebra. All these things we can study differential equations over. And, of course, we can always look for Eigen Solutions, right? So we always can look for Eigen Solutions in the sense that we have, if R of zeta is equal to e to the lambda zeta, let's say u, with AU equal to lambda u, if lambda is an eigenvalue, then that's a solution. And that's true even if lambda is in the spectrum, right? In fact, when you get into the algebra here, I think, the characteristic polynomial, well, more to the point, a minus lambda I times u equals to 0, right, has non-trivial solutions whenever the determinant of a minus lambda I is an element, in my notation, the zero divisors of A, which I think would be z of A union 0 in the book we were looking at. But now that's the characteristic polynomial, right? This is PA. Oh, I'm sorry. Old habits die hard, So PA of x would be the determinant of xi minus a, right? The characteristic polynomial. And so lambda in the algebra such that PA of lambda equals to 0 implies that lambda is a root. I really should start using some matrix other than A here, but it's too late. I'm too far in. But if we ever type this up, we shall not use A as the coefficient matrix, shall we? I don't know. We got to use some other letter. Or I should stop calling it A calculus and start calling it B calculus. Or X calculus. X calculus. Or what would make for an inordinate number of ever so conveniently placed puns, Z calculus. Yeah, Z calculus, yes. I mean, typically, my collaborator uses Blackboard A for the algebra. He tends to use this for the algebra, which is not bad, except that when I write, well, it's actually not bad. That's probably a better choice of notation than mine. But anyway, I'll probably be co-opted to that eventually. But all right. But on the other hand, if we have lambda in A such that P of A lambda is an element at the zero divisors of A without 0 in there, all right. There's the cost of my notation, because I'm saying a non-zero zero divisor, right? Then the then AU is equal to lambda U for some U where U is not linearly independent. Actually, I'm not sure that that's actually true. I just keep seeing it. It's true in examples I look at. Okay, this is the state of affairs. Some other things we know, just to set the table. We know that if we look at the matrix exponential, e to the, ZA, that the determinant, that ddz of this is a e to the ZA, right? Which implies that if we look at, think of x of z as e to the ZA, that this is a solution matrix. It's a solution matrix, and more than that, it's invertible because the usual calculation still makes sense. We can still say e to the minus ZA times e to the ZA is equal to e to the 0, which is equal to I. Because, because this and this commute. Is that true? That's true. Even, look, that's still going to be true even when the algebra is not commutative. See, because I just have to filter the minus from one side to the other. I was worried that I actually have to flip the z, I mean, in a non-commutative algebra, right? In a non-commutative algebra, if I had z1, if I had z1 here and z2 here, it wouldn't necessarily be equal to, let me get rid of the minus for a second here, z2a, z1a, because I'd have to, But that's not the problem. We have to push the minus from one factor to the other. So those matrices, zeta A and minus zeta A, they commute with each other. And so I think, this is the thing, maybe I'm overreaching my bounds. I'm not absolutely sure that if we look at a matrix with non-commuting entries, that the Baker-Campbell-Hausdorff technology still works. I may be overstepping my bounds. I actually have to think about this more to see whether or not I'm really convinced the matrix exponential still. I want to say the matrix exponential still is well defined and still is invertible, even when we're filling the matrix even when we're looking at a matrix of non-commutative elements. But I must admit, I'm a little bit concerned. I don't know. But that's, I'm getting distracted. So my point is, that is, at least in the commutative case for sure, that's a way to construct the solution matrix, right? And as long as we talked about the theorem, as long as we have enough roots so that we can string together the eigenvectors paired from root, let's call them root vectors. If we can put together the root vectors, if we've got enough of those to make a basis for AN, then we can diagonalize the matrix, And from our perspective, a differential equations perspective, we can build the fundamental solution set from Eigen Solutions, right? In fact, we could also work with a matrix exponential, right? If you had beta inverse, right? E to the zeta a beta like that. It's commutative. I'm assuming commutative. We could still do this usual calculation. That's really the exponential of beta inverse. Put the z up front, a beta, right? And so that would be exponential of zeta. And then this, of course, is the diagonal matrix with the roots down the diagonal. And that would just be e to the lambda 1 zeta, e to the lambda 2 zeta, e to the lambda n zeta, which of course makes sense because in the eigen coordinates, I mean, anyway, that's what the matrix of the thing looks like in the eigen coordinate system. But, anyway, so my point is, if we can diagonalize the matrix, of course, we have pretty good control over what the matrix exponential looks like. We can do a similarity transformation to rewrite it in a pretty nice, we can actually see it as just the eigen, the eigen solution stacked, concatenated, right? But the question that was on my mind was, what if you don't have enough roots, right? So one of the questions I was thinking about asking was, what do we do? How do we proceed if we're working over an algebra and we face an example where our characteristic polynomial just doesn't have zeros in the algebra, right? So what if, the roots of A, let's say the size of it is less than n. If there's less than n roots for this, I mean, the determinant's an nth order polynomial, right? So we still have a factor theorem. Each root corresponds to a factor. But you lose other things like uniqueness of factorization. But I think we still have a factor theorem. There's a claim, okay. But what if there are no roots? That's the most dramatic case, right? What if there's no roots? What if there does not exist, lambda in A such that PA of lambda equals to 0? What do we do then? How should we solve the system in that case? I mean, that's a good question. Is there always, in the case that there's no zeros, are there always zero divisors that work? I don't think that there's a dichotomy there like that. I don't think that's how it is, because here's why I know that. Suppose we're looking at A equals to 0, minus 1, 1, 0 over the reals, right? Then the characteristic polynomial of A is x squared plus 1, right? No real roots. No zeros in R. And it's real numbers, so there are no zero divisors. So I mean, we could still calculate the matrix exponential here. And in fact, I have you guys do that in linear. Pretty typical homework problem, right? I'll say, hey, calculate e to the TA, And you work it out, right? And what's it work out to? works out to cosine t I plus sine t times 0 minus 1, 1, 0, if I remember right. Because you can hack the calculation. I mean, that 0 minus 1, 1, 0 is j, where j squared is equal to minus the identity. So all the even terms grouped together to be plus or minus the identity times stuff. All the odd terms plus or minus j times stuff. And this stuff has the requisite factorials to pick up the power series for sine and cosine. Sorry, I worked a homework problem in your past. But that's great, but you know, this is little comfort to me when I think about solving a system of differential equations over the hyperbolic numbers or something where, you know, calculations aren't so pretty. So I have various ideas. Here's the two. I'll tell you the two ideas I have without writing. The one idea I have is that maybe we should just look at the extension algebra. I said I wouldn't write. It was a lie. We should look at something like a prime that's formed by a of k mod p of k. So just mod by the ideal generated by the characteristic polynomial of a. That algebra is custom built to make the characteristic polynomial have 0. So that extension algebra has a root, possibly more than one, to the characteristic polynomial. So I at least get, and the thing that's interesting about that is when I do look at that, and when I solve the system over, when I extend the system to this extension algebra and I solve it, my solution will no longer be an algebra solution. It will be an extension algebra solution, and that extension algebra solution will have in it, if I understand things correctly, most likely that extension algebra solution will have in it n regular algebra solutions to rip off, to steal. That's one approach.
And that's kind of like how we do, like, when we extend like the reals to the complex to solve the same thing.
Right. Yeah. Yeah. Exactly. Just like the complexification procedure we use in the real case. Now here's the other. Now, of course, I've already done this extension algebra idea for nth order system that Nathan came up with in summer 2016, and we worked it out. Right. Now I'm suggesting doing the extension algebra for systems. That's different than what I've done before. I might have done this before. I don't remember. I don't think so, though. The other direction we could go, though, would be just, you know, this is a system. Can we always take a system and rewrite it? Maybe this isn't true. When can you take a system and rewrite it as an nth order differential equation? The other direction is true. If I have an nth order differential equation, I can always make reduction of order. I can use reduction of order to change an nth order differential equation into n first order differential equations. Do you guys know about that? Let me remind you. I think reminding you will be useful here because it'll help us understand the difficulty of reversing the process, right? So, for example, if we have y prime prime plus prime 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 plus 3y prime prime plus 2y prime plus y equals to 0, I let y equal to x1, I let y prime equal to x2, I let y prime prime equal to x3. That ought to do it. So x1 prime is x2, x2 prime is x3, and x3 prime is where the fun is, which is y prime prime prime, but y prime 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 is minus 3y prime prime, which is x3, minus 2 x2, minus x1. So this gives us the so-called complementary matrix to the system. x1, x2, x3. I know you guys have all seen this before, but I think it's helpful for us to just write one out to try to get it in our system. 0, 1, 0, 0, 0, 1. What's that? To what in your system?
Is that a fun? To get it, you just said to get it in our system.
Oh. get in our system. Yeah, yeah. Thank you. Thank you. I miss you, Jess. No one sees the world through pun-colored glasses quite like you. Let's see here. Let's see here. But the point is that this matrix is actually kind of a special type of matrix. It's a matrix. Is it though? I don't know.
I don't think that's the companion matrix. Doesn't the right column all have to be ones in the companion matrix? Or am I thinking of something else?
It may be the transpose of what's been called a companion matrix, whatever you've been looking. And you may be thinking, and you may be thinking about yet another use of the word companion matrix, because you can imagine that people in various applications would use the terminology companion matrix to mean rather different things, right? Somewhere there's a developmental psychologist who will talk about the companion matrix for your mate. You know, this is score the companion matrix to see if you're compatible, right? Sorry. Whenever I look for topology books, I always run into this book entitled Topology, which has got nothing to do with topology. There's some kind of artsy person who's used topology for the label of their book, and it's not a math book. It's like, no, it's not like a topography misspelled kind of thing. It's much more out there than that. Next time I'm shopping for topology books and I run into it, I'll try to send you a link. Make it a required text. Yeah, I should have us put it in the library, shouldn't I? Yeah. It's the kind of thing, though, that might, who knows what kind of, I don't know. You start getting books like that, they might have things in them that, yeah, who knows. Yeah, art books. Anyway, I don't think that this is actually a hopeful, okay, so to invert this procedure, see if I could take my system and convert it to an nth order problem, then I could use my already existing tools to solve nth order AODEs. See, I have a machine to solve any nth order AODE. But I think there's a critical failing to this idea, which is that it's not possible to take an arbitrary, I mean, you guys here, just to be more explicit, x1, x2, x3 prime, 1, 2, 3, 4, 4, 0, 1, 0, 1, x1, x2, x3. Okay, now rewrite this. Rewrite this in the form y prime 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 plus a y prime prime plus b y prime plus cy equals to 0 for appropriate choices of a, b, and c. Is it possible? If it's similar to what? Maybe I just don't, maybe I'm just rusty in my linear algebra. It may actually be possible. I mean, we can always, there's a corresponding, I mean, that's a matrix. We can calculate the characteristic polynomial. By the way, do you know what the characteristic polynomial of this is?
Oh, isn't the roots in the bottom right there? Negative 1, negative 2, negative 3. So in the characteristic polynomial,
The point is, if this is a, then PA of x is actually equal to x cubed plus 3x squared plus 2x plus 1. That is not an accident. So if I was to try to do this, I would think about this being, let's say, b. You know, I calculate PB of x, right? And then if I had to, I would guess that there might be a change of coordinates, which I don't want to find. And with respect to that change of coordinates, perhaps I can recast this system of first-order differential equations as a single third-order problem. Actually, I don't know. I'm forging ahead into uncharted territory for me, actually. This is something slightly outside the scope of differential equations. And I'm embarrassed to say it shouldn't be. You know how many times I've taught differential equations? I was filling out my end of year report, and I happened to notice that I've taught it 13 times here. And I've taught differential equations a half dozen times before I came here. Oh, excuse me, the 13th time is happening in the fall. It includes fall numbers, but that's a lot of differential equations. And yet I don't know. I'm not sure about this. Well, anyway, even if it's possible, it's horribly ugly. And I think I prefer to attempt to flesh out my first proposal. Yeah. But you guys, that was what I had to say today. I mean, I can start working on that. But did you have something else you want to think about, or?
I had ideas to look at, but I feel like some of this might be like we might have done better if this is out of the way.
Okay.
Just thinking, I mean, like when we're in linear algebra, the natural thing to go after we think about like eigenvalues and eigenspaces is
Uh-huh.
the things like special forms or Jordan forms or Jordan forms.
Right.
Canonical forms, things like that. And I was just thinking that since we construct like the Jordan canonical matrix out of like block matrices consisting of the eigenvalues.
Right.
I wonder, since like last time we saw the example, we saw like two sets of possible eigenvalues.
Right.
I wonder if when we build like, because if we put those together, we probably get two separate Jordan forms that we can make like out of those.
Well, and I think those would be the Jordan. I mean, when it's diagonalizable, that is the Jordan form,
Yeah.
right?
But they would be different matrices, right? And then I mean, it might be interesting to see how they're related if you look at both like block diagonal forms. Just find out. It's probably something simple, maybe, but we need to look at. But I feel like that probably requires a little bit more development.
I think that's actually somewhat connected to what we're trying to do right now. And I mean, what we're trying to do right now is, in some sense, a generalization of the real Jordan form. The real Jordan form has to do, of course, with when it's most interesting when your real matrix has complex eigenvalues. You still can find some sort of canonical shape to match it up to with 2x2 blocks of rotation matrices, and then, of course, the regular Jordan blocks. And then you also get the tensors of the rotation matrix blocks and the other thing. But was it? So, okay, let me. The rational canonical form? Right. Yeah, the rational canonical form, we'd have that. That's here to work with, because the algebras we work with are real algebras, which means that they have the rational subfield. So I think the advantage of the rational canonical form is, despite its ugliness, it's general. I mean, for example, over the rational numbers, if you find that the characteristic polynomial is an irreducible, and there are irreducible rational polynomials of arbitrary order, the Eisenstein criteria creates these nice examples, right? We've seen these. So that means that if you have a matrix that has an irreducible characteristic polynomial over the rationals, then the corresponding rational canonical form is that same size. And that maybe is the one you're thinking about, Jess. It's got like the coefficients from the next to leading coefficients of the characteristic polynomial in the last column, and then ones, depending on how you set it up. It all depends on how you build the cyclic basis that builds the canonical form. Ask me in about 3 weeks. Maybe I'll be into that in the 422 course. Yeah. It's all based on unique factorization is true. Huh. Oh, but there's always a standard form, right? Well, the characteristic polynomial, we can always write it as a sum of monomials. Like x to the n, coefficient times x to the n minus 1, so forth and so on, right? And I think you can always take that, and if you use the build the cyclic basis, then with respect to that cyclic basis, the matrix of that transformation will have the form of the rational canonical, the rational matrix corresponding to that polynomial. Whether or not that polynomial can be factored, I think you can do that. However, if the polynomial can be factored, you can further break down these matrices in other interesting ways. So, given the factorization, then you can instead of just having one big rational, quote-unquote rational matrix, you can have blocks of rational matrices corresponding to the irreducible factors, something like that. Or, like I said, in about 3 weeks I'll be into it in 422, so let me wait till then to say more about that if we need to.
But your cyclic basis is actually a basis if you have if you want to, but not on general.
Oh, the cyclic, I don't even get, my cyclic basis argument breaks down, you say?
Yeah, breaks down when you get over it.
Really?
Yeah, so it's like in general.
Hold on a second. Hold on. So if we have t going from an to an, let's say, right? A in algebra over R for our discussion, right? So I say I pick x not equal to 0 in an and form, let's say beta sub x, t of x, t squared of x, ... So you're telling me that that does not form a basis for there is no notion of cyclic subspace generated by x under t?
More like free.
What happens? Why does it break down?
Because you may like you have a when you calculate the characteristic polynomial, you have only you have a first coefficient. The highest one is always 1. But there may be like smaller polynomial with coefficient different from 1 that like satisfy the t. I mean, when you plug in t, it will be equal to 0. It's like maybe it has something to do with zero divisor.
Something to do with zero divisors, right? So can we think of an example of this, what the trouble is? Like, can you tell me, for example, let's look at a equal to the hyperbolic numbers for the sake of discussion, because I'm, creature of habit. It's not a good habit, but it's a habit. And let's look for maybe two-dimensional?
I don't know how to construct with linear transformation, but I just say like.
You just know from looking at the characteristic polynomial.
No, I mean like for single polynomial, like do you remember what I said about the normalizable polynomial?
I don't have it. It's not. I haven't internalized. I vaguely remember, but.
So it's like a polynomial with this zero divisor as the leading coefficient.
Okay.
But you can multiply it with some other polynomial to make it into a
Oh, so this would be normalizable.
Yeah, so it's like.
But you have to you have it something so like 1 minus. So you put a g of x over here, right? And it's hard to think about what that g of x should be. But your concept of normalizable is I can take this f of x, multiply it by the appropriate zero divisor, and then 1 minus j times g of x.
No, I mean like multiply with some polynomial.
So with some polynomial. So it's not the zero divisor. I can multiply this by h of x, such that this is monic. So there's something happening inside. There's something in h of x that conspires to remove the offending degenerate maximum term.
So if you take x as x to be some roots of fx,
take x, take a root of fx, yeah?
Then you would have a relation like, I mean, what
So let's use lambda for the sake of, so you have f of lambda would be something like 1 plus j lambda squared plus g of lambda, I guess, yeah?
so you have like,
Oh, suppose that's 0. Okay.
so you generate 1 lambda, lambda squared, lambda cube up until some constant because you can multiply x, fx with hx, turn into a polynomial. And when you plug in the lambda into h and f, you will have a 0. F lambda is 0. I mean, let's say f.
So this would say that h of lambda times f of lambda is equal to this monic, which is lambda to the whatever n plus stuff. Oh, but that's very troubling because then you have.
Yeah, you, like I said, like 1 lambda, lambda squared, lambda cubed to the lambda n minus 1 is like a cyclic basis thing,
Mm-hmm.
but they still have it.
I really need to reread your paper again. I'm sorry, gang. I'm not up to speed on your. Not up.
Or how it might not work for the motor like stuff by looking at just like.
But you're pretty sure from your work before that the T cyclic basis idea breaks down. Okay. All right.
I mean, I can take like I can take t from a to a when like setting n equal to 0, n equal to 1, and we got the second as a.
Oh, you can. You have a counterexample for n equals 1. What was it? T of z equals to what? Will be my n equals 1.
X times
Fix an x, just any x.
yeah, that big X.
So like 1 plus j times x times z. Would that work?
Yeah, it's true.
Oh, so if I look at, so pick any z not equal to 0, right? Then if I look at z naught and t of z naught and so forth and so on, this is the set z naught 1 plus j but it seems to me that I still have a,
I mean, you got to divide. It cannot be a basis.
well, okay, fair enough, but the idea of the T cyclic basis is that we can go, it's an inductive idea. So we start out with a non-zero vector, and we go as far out as we can, maintaining linear independence.
Yes, but
And so here,
you may not have a free one.
but here all I have to do is pick z naught not to be, if z naught is not a zero divisor, then my T cyclic basis here would just be the set containing z naught alone. So I don't think this, in my thinking, this doesn't constitute a counterexample, because holding to the spirit of the T cyclic basis idea, which is that we go as far as we can, maintaining linear independence. But your point is that there are other examples where, but I think we can always start, if we always start with, I guess
I mean, you said that x is not equal to 0.
okay, so here's the problem. I think I see what I think I start to see the issue. So great. Suppose you're in a higher dimensional example. You pick your vector, whatever it is. Let's say z naught vector, all right? And then, great. And then you pick your t of z naught, and so forth and so on. So the point is that this can have multiplication by things which forbid it to be part of a free module basis. So inclusion of things past that point automatically means that there's a linear dependence. And it also means that I can't write higher powers of, so the problem is I can't write higher powers of t in terms of lower powers of t.
Well, you can because of the Cayley-Helm principle,
Oh.
but there still be like lower polynomial,
Ah.
lower polynomial.
Oh man. I need to find a better path through the wilderness here to structure our conversation. Because I mean, this is good, but I need to find some structure here to gather these results together because we're kind of bouncing around. But thank you. I think this is helpful. Can we? Let me try my silly quotient idea for a minute here while it's fresh on my mind. So I think that to summarize our conversation so far, we're not sure about what happens to the Jordan form over an algebra, if there is such a thing. Except that what? Except for a division algebra. Except for a division algebra. Ah, I see. All right, so we start with the problem dr d zeta equals to AR, right? And we're looking for a solution R that goes from A to AN. That's our starting point. But then we're saying, well, suppose, actually, honestly, if my previous experience is any guide, what I'm about to do will not only solve the problems that I've identified as escaping our Eigen Solutions, it most likely will also solve all of our problems in a somewhat heavy-handed way, if we're lucky. But the point is, we can calculate the characteristic polynomial of A. As usual, it's the determinant of xi minus A. Okay, so this is an element of, well, it's an nth order polynomial with coefficients from A, right? Or perhaps this is better written as A of x n, n less than or equal to n. Yeah, that's why that notation isn't as awesome as I want it to be. But maybe just less than or equal to n. There we go. That'll work. So up to nth order polynomials in A with indeterminate x. Yeah. Okay, anyway, setting aside stupid notations for this thing, who cares, whatever. The point is, I suspect that we could work on A prime, which would be the algebra polynomials in the, so we'll do polynomials in K over the algebra mod the ideal generated by this thing. And what this looks like, of course, is something like A0 plus A1K plus AN minus 1, K to the n minus 1, such that A0 through AN minus 1 are elements of the algebra. In other words, I'm claiming that, in fact, A prime is a free module. It's a free A module of dimension n. So up to isomorphism, this is essentially just AN, right, as A module. It's an n-dimensional vector space over the algebra is my point. Although that's in abusive terms, because the algebra is not a field. It's not a vector space, it's a module. All right, fine. All right, so in this context, I have a suspicion, which is that if I have, so now I'm looking for R, let's say R, for lack of a, oh, you know what? I should not have put a vector on this R before, because what I want to do now is put a tilde on this one. And I was once scolded for putting a tilde over a vector in my junior level mechanics class, and it's forever left me scarred.
What's the tutor?
I don't know, but the mechanics teacher was incensed. He was like, you can't put a tilde over a vector like that. This doesn't even make sense. See, because physicists, they have a physical interpretation for notation. And when you violate it, you're violating their physical intuition sometimes, if that's how they think. they hold notation much more deeply and dearly than we do. Beware of this if ever talking to a physicist. You might think you could write a dot or a prime. They might disagree with you. Anyway, R tilde. I'm suggesting that this is a mapping from A prime to, goodness gracious, I want to say A prime to the n, yeah? There's two uses of n going on here. We're talking about, and they are, it's not a mistake on my part. There are n different, we're looking at a system of n equations. So for a system of n first order equations, the characteristic polynomial is nth order. But this is starting to be kind of a big thing. I mean, this is n squared dimensional over A. That's big. But I think we want this such that what? Such that dr tilde d let's say zeta tilde is equal to A r tilde. Notice that A is also an element of A prime n by n. Since A n by n is naturally viewed as a subset of A prime n by n, since A is a subalgebra of A prime. In particular, A is identified as the constant terms, the terms, if you wanted to think about it, the terms with k equal to 0. That's not quite the right thing to say, but because I don't really think of k as a function. I think of those as placeholders in the extension algebra. So if we could solve that extended problem, right, then my suspicion is that that solution, right, that whatever the solution to the extended problem is, will have components. It will have components which are solutions to my original problem. How do you solve the extended problem? Can we solve the extended problem? Why can we solve the extended problem? What's that? So the extended problem, right? Let me use a tilde just to be obnoxious. P tilde A of x is what? It's still the same, right? But, here's the big thing. P tilde A of k is equal to 0. The extension element, k, is, by construction, a 0 of the characteristic polynomial. In A prime, the characteristic polynomial has a 0. Right? So then, if the characteristic polynomial has a 0, does that mean that there exists an eigenvector? Oh yeah, well this is there's a root to the characteristic polynomial. Does that mean that, I mean, I think that, now this is what we got to be careful about, guys. I think this means that that there exists, let's say v tilde not equal to 0, such that A v tilde is equal to k times v tilde. That's what I got to think about more after today. Make sure I'm not tricking myself on that. All right, that's the step I'm worried about at the moment. But if that step is reasonable, where is v tilde? here v tilde is, it's an element of A prime, it n tuples in A prime. In the extension algebra, we can find an eigenvector where we couldn't find one over the algebra itself. And so, if we look at, R tilde being e to the what? E to the k, zeta times v tilde, this, how does this work out? Well, more specifically, this is R tilde of what? Oh, at this point, I'm doing something special, right? Okay, excuse me. So, R tilde of zeta tilde, right, would just be e to the k zeta tilde times v tilde, right? Great. That would be a solution on the extension algebra. That's not actually what I want, though. See, so then here's the trick. Here's the trick, is that if you have this, you can just as well write this. Algebra variable. And then I have e to the k, the algebra variable, v tilde. I believe that's still a solution to the different system of differential equations in a certain sense. It's an n-tuple, actually. Let me explain this more fully. So here R tilde of zeta, right, is actually R1 of zeta plus R2, or let me say R naught of zeta, plus R1 zeta times k, plus plus Rn minus 1 zeta of k to the n minus 1. See, this extension solution, if I evaluate the extension solution at a algebra variable, which is restricting, really. I'm restricting the extension solution to the algebra, which I can do. If the extension solution exists for the whole extension algebra, I can restrict that solution just to the algebra itself. That's that's a reasonable step. And in so doing, I can look at the component functions of that restriction, and I get 0, 1, all the way out to n minus 1 component functions to the extension solution, right? The derivative of these is done component-wise. So it's like, R naught prime plus R1 prime k, Rn minus 1 prime k to the n minus 1. So like going back up to here, you've got something like, R naught prime plus R1 prime k plus Rn minus 1 prime k to the n minus 1. That's my this, and that's equal to A times R tilde, right? Because, again, the construction of the solution is done in the extension algebra, so it is a solution. But if you have a solution in the extension algebra, that entitles you to n solutions in the original algebra, because you can distribute. And this is where it's important that A and so you notice that this, these are all in the algebra itself. The extension element k is manifest. Did I use alphas instead of k? my, where does alpha come from? K, all right? And so the point is, for these two things to be equal, because 1 k, k squared, da da da, kn minus 1 is a free A module basis, we can equate coefficients. And this implies that R naught prime is A R naught, and R1 prime is A R1, etc. Rn minus 1 prime is A Rn minus 1. So what I'm arguing is that the component functions of the extension solution are separately, the component functions of the restriction of the extension solution to the algebra form n solutions to the problem. How do you actually calculate them? How do you calculate these R0, R1 through and so forth and so on? All you have to do is multiply the exponential by your extension eigenvector, your v tilde. So what that actually looks like is, see, this is C plus ks1 plus ks2 da 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 plus ksn, n minus 1, I suppose. And that to the n minus 1 squared. And that's going to be equal, that times, right, that times your v tilde. V tilde has the form, let's say v naught plus v1k plus v n minus 1 k to the n minus 1, like that. And then, so all you got to do is multiply it out and collect coefficients of like powers of k. Those are your extension solutions. Of course, the most familiar case of this is when we work over the complex numbers, right? You have something like e to the kt times a plus ib vectors, right? This is what you're most used to. This is, but this is essentially the R tilde idea, where k squared is equal to minus 1. So this is cosine t plus k sine t. I mean, we have the other names for the special functions of the exponential here. That's the motivation for the k's. That's the motivation for me using c and s's here. They're sort of the generalized cosines and sines of the algebra. I think I call them the special functions of the algebra in the paper. But you see what we got. We got cosine t a minus sine t b, right, plus k times cosine t b plus sine t a, right? You recognize that, of course, from the course in differential equations, right, where we do the complexification solution. I hope I've shown you today that that idea generalizes. Whoa. So now the problem becomes, so King, the real problem is how do we calculate? You see the problem now? We don't actually need to find a Jordan form, right? It suffices for us to learn how on earth do we actually solve this, right? If we can give a decent answer how to solve the generalized eigenvector problem over the extension algebra, then that suffices to build a standard solution. It's ugly. It's really ugly. You know what I'm saying? Like, this is nice. K times k, k squared equals to minus 1. Yay! You got to understand, over here, when you have k to the n minus 1 times k, right? That gives you k to the n. K to the n is not equal to minus 1 here. K to the n is equal to minus all of the rest of the junk in the characteristic polynomial.